Hopefully the computer has enough space. Okay, so review session number 1. First thing I'm going to do is I'm going to ask everyone to head to Schoology. All right, so first thing I want to talk about, a quick rundown. I'm going to spend most of my time talking about our main topic for today's review, which is going to be the first 2 units, which are kinematics and projectile motion. But I wanted to quickly run through this because I haven't had a chance to do that yet in class. This is the folder preparing for the AP exam. It's got a lot of great resources, some of which come from your textbook, which is completely designed to get you as prepared as possible for the AP exam. So I would definitely be using your textbook or review book, whatever you want to call it, for a lot of your studying, okay? And at the top, I make a note here. If you need an answer to any of the problems on this Schoology page, please message me. I've gone through and made it so you can look back at all of the tests and all of the quizzes and everything else we've done this year. So you have problems to look at as you study on these last few weeks. If there's ever a question where you're studying and you're like, man, I think I got this, but I have no idea what the answer is, and you just want to check, just send me a Schoology message. I will send you the answer to the question right back to you. Now, we're going to find the stuff we need for today in this red folder called AP Review Sessions. I'm going to be posting notes, and I'm going to be posting questions, and the questions are mostly what we're going to be going through each review session. They're questions I write myself that kind of cover the vast majority of ideas in each unit. So hopefully there's enough in there that you guys have a solid understanding of each unit or a good refresher to at least ask questions as we get closer to the exam. We're also going to do a lot of stuff with this in class, but obviously the more we do, the better. So AP practice exam multiple choice. I believe this is the assignment I've given you for Friday, and except this one has all of the questions that aren't cut off. So this is a option for you to have experience with AP multiple choice questions, and trust me, you're going to get a lot more of them before the exam. This is a PowerPoint slide, Ultimate AP Physics Notes. Basically, this is a PowerPoint presentation I made for the students last year, which is basically a mini textbook, kind of like there's a slide for each major topic, and it highlights the important equations and the important ideas you have to go through. So going through this and making sure you understand what's on each slide is going to give you a leg up for the exam. Obviously, AP reference table, which we need to get used to using. I know that through a lot of my teaching, the AP reference table was not necessarily required, especially when a lot of my tests required you to use notes. But we need to get used to having the AP reference table next to you while you're doing these problems, just so you are used to the things that are available, because those equations are the ones that they know you're going to have with you. And so those are the ones that are more likely to ask you questions about. AP review channel. So the AP College Board organization does tons and tons and tons of video lessons. They live stream them very often. I don't really know what the schedule is, but if you need review on a particular topic and I haven't given you enough on that topic and you want to go look for some other lesson, they break down the different types of test questions. They break down the different units individually, so you can get a stronger understanding of whatever units are most troubling to you. Especially if for some reason my teaching is not to your liking, you can hopefully find another teacher from that the AP has made a video with that is going to help you understand the stuff. Preparing for the AP exam. This is a PDF export from your textbook. There's a section near the middle back that basically outlines what the exam is going to be like, and it gives you tips for how to prepare and basically tells you what to expect. So here's the main thing. There's going to be a part 1, an hour and a half, multiple choice questions, okay? 45 of these will be single select answers, meaning that you'll have to choose between A, B, C, and D. And 5 of the questions will be multiple selected. So that means you might be picking 2 or more answers for each question. Watch out for the ones that require you to answer multiple, because I have people occasionally just give one answer for everything. And so it's a challenge of reading the questions, making sure that you understand how many answers you are supposed to give. There's no penalty for guessing and answering incorrectly. It's better to fill in all the bubbles than to not fill in the bubbles. So some tests, I think, like the SAT, might punish you for guessing, or at least they used to. The AP exam won't. So if you got 5 minutes left and 10 questions left, it might be better to do the easy ones and then just guess on the ones you didn't have time for. Free response, you're going to have an hour and a half for that one as well. So there's a little bit of a break, and then in total, you're going to have 3 hours of test time. You may use a calculator. I looked up the calculators that you're allowed, and it's basically all of them, okay? Especially if it comes from Texas Instruments. Even graphing calculators, once you can program, there's really not any calculator that they say you can't bring. But in case you need that information, I have a full list of the approved calculators. So if you just send me a picture of your calculator, you tell me what brand it is, I can make sure it is good to go for the exam. And if you don't have a calculator, I would let you borrow one from my classroom, if you needed it. So like I mentioned, there will be 5 questions on the short response section. 3 of these are worth 7 points each, with a suggested time of 13 minutes. There are 2 worth more, and they give you 25 minutes to do them. Now, these are suggested times. You can spend all of your time on one of these 5 questions, but I don't think that would be a very good strategy. Now, adding up the points here, the short answer questions or the long response questions add up to 45 points, but those 45 points still count for 50% of your final grade on the exam. Okay. Now, one of the 12-point questions, one of the longer ones, is going to be an experimental design and critique questions. Those are the questions we would go over where you had to design an experimental procedure, making sure to provide enough detail that other students would be able to repeat the exact experiment with the same exact procedure as you. When it says critique, that's normally talking about the questions where they'll say, okay, a student did this for their experiment. What did they do wrong? Or what could they have done better? We've done a few examples like that in class, and we'll do some more before the test. And the last one here, there will be a paragraph question, very similar to the kind of questions we were doing today in class. For those of you who missed, we did a question where you had to write a paragraph as to where you should hang little masses in order to get a certain amount of torque that you want, or something about explaining which location would give you the most torque. Either way, a paragraph response normally requires you to explain your answers with words, and sometimes throwing in equations will really help clarify your point, and they often look for that, and they might give you credit for including a equation. The biggest thing with all short answer questions is that you do not want to write down anything you don't know is true. So if you're like, I'm pretty sure this has to do with torque, but I'm not really sure, you can describe it exactly the way you understand it, but throwing out a word you don't really understand yet might be dangerous, because if you provide incorrect information or you use a word wrong, that can take points away from your answer. So you really want to make sure that when you are writing your answers, you write down the stuff you know is true. Keep your answers short and sweet. Don't write too much, because that just increases your chances of getting a wrong answer. You want to fully answer the question and provide good detail, but don't just write a page and just try to get all the little answers, because they will penalize you for wrong information. So that's just a little bit of a test overview. They go through some frequently asked questions here. If you read this or you have questions about it, I will happily talk about it. And I could talk about it in class as well. It goes on to say, you mostly need about a 70 or 75 in order to get a 5 on the exam, because the exam is going to be quite difficult. But it doesn't quite work out like that. The AP exams are graded very, very weird. But in general, if you can get 2/3 or more of the questions correct, you're going to do quite well on the exam. So shooting for the moon. All right. So let's get to the stuff I want to do this week, which if you look at this AP review sessions folder, I've got notes for the section that should be available to you, and also problems. I'd like you to open up both of these documents. I'm going to start with this one, okay? So what I want to do, these are not long notes. And if you are writing them down, don't really stress about doing that right now, because you have access to this PowerPoint, okay? It's very short and sweet. It's going to be highlighting things that I think are important about these first 2 units, which are kinematics and projectile motion, okay? So these are the main things I think you got to take away, and then we're going to spend the rest of the time looking at 3 problems, and I say 3 problems with a ton of extra parts that are going to highlight the key skills that you need to have in order to master the questions in this topic. So very briefly, this is a little blurrier than I would have liked, but these are sets of equations. These are the equations that really matter in terms of these units. So if you look at your reference table, they give you these 3 equations, and they're in very, very unusual forms. When they're talking about x and x naught, x with the little 0 is called x naught. They're talking about initial position and final position, okay? The reason they show it with a little 0 is that they're saying position at time 0, and then your position at time whatever. Now, normally what they do is they subtract the initial position over final position minus initial position is going to give you displacement. And so normally we just write this as D is equal to VIT plus 1/2 AT squared. So this is what the reference table gives you, the ones on the side. These are the easier forms we use in class. The easier forms we use in class are totally fine for the exam. These are perfectly okay. So there's no reason to use these equations unless you like them better for some reason. If a problem gives you initial and final position, you might want to use these equations because it could be helpful. But the easier forms here are totally fine. And if you're more comfortable with them, which I am, I would be using those instead. Now, over here, I've got equations that hopefully make sense to you, but they're not on the reference table, and they are definitely something you are expected to know. The first one, average speed or average velocity is equal to distance over time. I guarantee you, all of you knew this one. I know it. I have so much confidence in you that you got that one down, but for some reason they didn't put it on the reference table, and so it's in this memorized column, okay? Also, acceleration is equal to change in velocity over time. This is a equation. It is actually just a rearranged version of this first equation, VF equals VI plus AT. It's the same equation, just written slightly differently. But I often refer to this as the definition of acceleration. If your velocity changes, then you have acceleration, and that's a key idea. And so I think it's important to remember it in its fraction form. Also, it's good to remember change in anything with that little triangle means final minus initial. Make sure you have that, because it could be change in momentum, change in energy. You want to make sure you understand what that little triangle symbol means. And lastly, average speed or average velocity is equal to final velocity plus initial velocity divided by 2. It's the one situation when you have a constant acceleration, you are allowed to use this equation. And that basically just means you find the average of the initial and final, and you get the average. Now, this makes sense. It's the only time an equation really makes intuitive sense when it comes to averages, because normally averages confuse everything. But this equation comes up a lot, especially if they're asking for the average something. So I think it's an important idea to have this memorized for the exam. So 1 second, gotta turn the lights back on. Okay, so a key idea that never really came up after the initial unit was distance, displacement, average speed, and average velocity. So you have to remember that distance is how far you've traveled, but displacement's only the difference between where you started and where you ended. So sometimes when they're talking about velocity, they don't really care how far you went. And so you have to keep track of whether or not they're talking about distance or displacement or speed or velocity. One cares about direction, one doesn't. What is it called when one quantity cares about direction? Someone answer this question for me.
It's a vector.
It's a vector, yes. So displacement and velocity are vectors. And someone answer this question. Speed and distance are what?
Scalars.
Thank you, Zach. Yep. So this doesn't come up a lot in the later units, but it is an important idea. Most of the time, though, they're going to be talking about displacement. And most of the time, they're going to be talking about velocity. But if they ever specifically ask for speed or distance, you got to remember what those words mean. Okay. And then you got to acknowledge averages as well. That's what this little line means above the V. It's average speed, average velocity, because I could speed up really fast and do this first half really quickly, and then take my time and go really slowly around the second half. Whoops. And therefore, my average speed would be slower because I was slower on the second half. It doesn't care how fast and slow I am going down the middle. If I plug in total distance over total time, I'm going to get the average speed each time. I won't get the final or the initial. I will get the average. Okay. That leads me into an idea that confuses me so much, but is so important. There are 3 speeds in every problem where there's an acceleration. If there's no acceleration, then you have a constant velocity and you only have 1 speed or velocity to worry about. However, in so many problems, there are 3 speeds you have to keep in mind. There is the initial, there is the final, and there's the average. And sometimes when you're doing a lot of math, there's so many V's to keep track of, it's hard to keep them straight in your brain. But you got to remember, initial is a lot of times things start from rest. It's very helpful when they do that, but they don't have to start from rest. There's going to be some acceleration, some change in the velocity, and then there's going to be the final speed at the end. And then to find the average, you literally just add them up and divide by 2. So the whole point of me making this slide is basically to say, make sure you keep track of these 3 velocities in your problems and you don't get them mixed up. Okay, a very common mistake is to plug in the initial where the final should go, or to think everything is average. You have to be careful there. All right. Now this slide has a ton of information, and it is included in the ultimate reference table that I pointed out earlier. Basically, there's going to be 2 main types of motion graphs, distance and velocity. And those lines, depending on whether they're curved, straight, and whether their slope is up or down or constant, it's going to mean different things for the motion. So for example, if your distance or position or displacement, decide if it's any of those things, it's all the same. If it goes up very quickly at a constant rate, well, then that's a constant velocity, but a fast one. If it did the same thing, but closer to the time axis, it would be a slower constant velocity. Whenever you get a curved line on a displacement versus time graph, that's going to be an acceleration. If it's curving up like this, it's going to be getting faster. If it's curving, if it's kind of flattening out, then it would be getting slower. But basically, you want to keep track of the slope, okay? Because remember, the slope on a distance versus time graph is going to be equal to your velocity. So here you can tell the slope is increasing because every second, the slope of the line is steeper. Now, an object is not moving when it's a flat line. It's got a constant velocity, see slightly slower here. And then here's a negative velocity where the distance is actually going down with each second. Then you can translate the same information to a velocity versus time graph, keeping track of what you're doing in each place. So all these straight lines, like this really fast green one and this really slow, the slower one, these are constant velocities. They would just be flat lines on this side. That's this red one here, constant speed. Because if your speed doesn't change, you don't have an acceleration, then you do not have a slope on a velocity versus time graph. They just mark off how fast you're going and it keeps that. When you have a slope on a velocity versus time graph, that's going to mean you're accelerating. Now, this guy, his velocity is going down, this green line. So this is a constant deceleration or a constant negative acceleration. If it's going up, you have a constant positive acceleration. And if it is doing this weird curve thing, you're never going to really see a curve in a velocity versus time graph, but that would mean your acceleration is getting faster, which is a problem they're never going to ask you. Okay. So any questions before we get started on some of the problems?
None here.
I'm there. Okay. All right. I feel like I'm going very fast and I don't want to do that, but we do only have an hour. So, and by now that's like 35 minutes. So let me panic some more. All right. Let's close this out. And by now, everyone should have these open. Now, I acknowledged the fact that it is very unlikely that we finish these. And so if you scrolled all the way to the bottom, the first 3 pages are 3 problems. The full solutions to all the problems are on the next 3 pages, 4 pages. So you don't have to worry about that. But I do want to try to go through these individually. Okay. So I'm going to walk through this first example, and then I want you to try the next one, and we'll see how far we can make it before we're out of time. All right, so let's stop the share. Here is my paper. And you should have this open in front of you. So hopefully the fact that this is like the worst camera quality in existence will not matter so much. Okay. So reading this problem, a ball of 5 kilograms is tossed into the air above an unknown planet. So that's an important detail. What would be the acceleration of a falling object on Earth? Someone answer that question for me.
9.8 meters per second squared.
Right, so normally
Negative.
acceleration, very good, Max. Normally the acceleration is negative 9.8 meters per second squared, but that's only for Earth. So that's not happening this time. All right. So we can't be sure what the acceleration is, but still the ball flies upward, slows down, and then returns to the person's hand. So you can think of it like this. Ball goes up, ball has a momentary pause, comes back down to the ground. What's the velocity of the ball at the very height of its path?
0.
0. They love to ask questions about that. So I'm going to say final, but I don't know. The velocity at the very top of a projectile's path is going to be 0, and that's a big concept for them. So the ball reaches a maximum height of 42 meters in 3.8 seconds. And then there are 4 questions. What was the initial velocity of the ball? What is the gravitational field strength on this planet? Basically, they're asking, what is the acceleration? What is the G for this planet? C, what are the average speed and average velocity of the ball from the moment thrown until the moment caught? And then lastly, make a graph of the ball's position versus time and velocity versus time graphs. Okay. So I want you guys, I'm going to give you 60 seconds to look through these problems and think about what you think the answers might be. Okay. So I don't need everyone to go through it fully, but I need you guys to just read them and think about if you know any answers right away. So I'm going to hit the timer here. 60 seconds, and then we will go over it. Okay, so hopefully you've had some time to think about it. Some of these answers can come really, really quickly, and some of them take a little bit longer to figure out. So option A, or question A, what is the initial velocity of the ball? So this is a common physics problem. I want a number. Tell me what this number is. So I need to get the initial velocity. Now, that means I have to look at the numbers that I do have and figure out a way with the equations I know to get to this number. So they gave me mass, 5 kilograms. They gave me height or displacement of 42 meters. Okay. And it gave me time of 3.8 seconds. So I have time, distance, or displacement for at least the way up. I don't want to confuse that with the 84 meters that it takes to come back down, but still. So we have that. We have the mass of 5 kilograms. We need to get to VI. So first thing I'm going to think about is, okay, what equations do I know that have VI in it? Well, I've got this one. VF equals VI plus AT. That one, I don't know A, and I don't know VF. Actually, I do know VF. I know VF because we said at the beginning that VF for the top of the path. So if I'm just looking at the traveling from the hand to the very top of the path is going to be 0 meters per second, because at the very top, we have no velocity. Okay. So we do know that, but we don't know A, and we're trying to solve for VI. So that's still 2 things we don't know in this equation. And so this equation probably won't work. Let's try another one. So VF squared equals VI squared plus 2AD. So again, we know VF. We know we're looking for VI. A, we still don't know it. And D, we know that one. But still, because we don't know acceleration for this planet, I'm still kind of stuck with this problem. So is there any more equations that have VI in it? I'm actually asking the room. Does anybody know one more equation with VI in it?
D equals VIT plus 1/2 AT squared.
Okay, so D equals VIT plus 1/2 AT squared. So I know the T and I know the D. I don't know the A again. So A is really hurting me here. So I need an equation that has VI in it, but does not have A, because otherwise I'm going to get stuck. And the answer to this is average speed is equal to VF plus VI over 2. This equation, which I asked you guys to memorize, doesn't have A in it, but it does have average speed, which again, I don't know. I wasn't given any of the 3 velocities. But I do also know that average speed is equal to distance over time, which I have distance and I have time. So this is the game. You're looking for an equation that has VI in it, that you know all the letters to. And if you find an equation that works, but you don't know something else, if there's another equation you can use to get that thing that you need, you can actually figure out the solution. So it's basically just playing a game, looking through the equations, trying to figure out which ones are going to work. So this in combination with this one will work. So I'm going to replace this average speed here with this D over T equation. So D over T is equal to VF plus VI over 2. VF is 0, so I'm going to get rid of VF. D is 42 meters. Time is 3.8 seconds, and that should be equal to my initial velocity divided by 2. So I multiply both sides by 2 and plug it into my calculator. And so 2 times 42 is 84. 84 divided by 3.8 gives me 22.1 meters per second for my initial velocity. Okay, so that is part A. Part B, what is the gravitational field strength for the planet? Okay, so in part B, we're trying to find what is the gravitational field strength. So we want to know the acceleration that is pulling objects down on this planet. So now that we have VI, we could use any of these equations before where we were only missing A, and we can solve for A. So I'm going to use VF equals VI plus AT because I think that's the easiest one. So VF again was 0 meters per second is equal to the VI that I had, 22.1 meters per second. And then I'm going to add A, and the time was 3.8 seconds. All right, so I have to subtract over that 22.1. Okay, and divide by 3.8 seconds. All right, and if you look, I'm going to get a negative answer, which makes sense because everything is being pulled downward, which is normally the negative direction. So negative 22.1 divided by 3.8 gives me negative 5.82 meters per second squared. Like that. All right. So that is my gravitational field strength, which is another way of referring to the acceleration due to gravity. If they call it that on you, I'm sorry. It's a little annoying. Anyway. So for C, we're looking for what is the average speed and average velocity of the ball from the moment thrown until the moment caught. So that means we're looking at this equation again. All right. So first, let's do average speed. So I know that it's traveling 42 meters to the top, and then it's going to take 3.8 seconds to get there. Now, it also takes 3.8 seconds to come back down, and it's going to travel 42 meters. Because remember, everything in this kind of a problem is symmetrical. So if it takes 3.8 seconds to get to the top, it's going to take 3.8 seconds to come back down. And so for average speed, I just have to take the total distance, which is 42 meters up plus 42 meters down. and divide it by the total time, which would be 3.8 seconds plus 3.8 seconds. That gives me 84 divided by 7.6. I think that's right. And so I'm going to have an average speed of 1105 meters per second, which makes complete sense when you realize that the final velocity is 0 and the initial velocity is 22. The average speed being 11 is right in the middle. Okay. Now for the average velocity, we have to take the total displacement versus the total time. So we know the total time is 3.8 plus 3.8. So that's again 7.6. Can someone tell me what the total displacement is?
0.
0 meters. Okay, it's 0 meters because we end up at the same exact height where we started. Going from all the way up and coming back down, we have no displacement, which means the average velocity for this trip, 0 meters per second. Okay, and you don't need to include a direction for this velocity because 0 in what direction doesn't really make any sense. And lastly here, D, we want to make a graph showing the ball's position versus time. So we want the displacement versus time, or the distance versus time is the same thing. And we want a velocity versus time. Does having the lights off actually make it easier to see?
It's pretty much the same.
Yeah, I can't tell a difference.
Okay, well, I'll leave it for now. So how is the position changing with time? At least initially.
It's gonna like go up
Okay.
like as a parabola type of thing.
Yeah, so initially it goes up pretty fast, right? Because it's tossed initially very quickly. So you have a steep slope. And then as the ball keeps going upward, it's going to slow down. So our slope is going to get a little shallower and then slow down a little more. So it gets a little bit more shallow until eventually we reach the highest point in its path and it flattens out. Once that occurs, it's going to start speeding up in the negative direction. And so we're going to get a little bit of a negative slope and then a steeper negative slope and then a steeper negative slope. And so basically you get this parabolic curve as the ball is slowing down as it rises and speeds up as it comes back down. How would I represent this on a velocity versus time graph?
It's gonna start positive and then like go down into the negatives.
Yeah, so it starts very positive because we're going upward. It's going to have a straight slope because remember, you're never going to need to curve a velocity versus time graph. You're always going to have a constant acceleration. And in this case, we have a constant negative acceleration. So it's going to have a negative slope going down. Once we reach 0, this is the same as when the ball is at the highest point of its path because the velocity is 0. But then we keep on accelerating at the same rate, coming back down to the person's hand with a negative velocity. And so this should be a straight, constant line going down past the 0 line like that. Okay. Any questions on this problem? Okay, so we have a little less than 20 minutes left. What I'd like you guys to do is to try to solve the second problem by yourself. Try not to look at the solutions, which I did provide you guys. In this problem, a tennis ball and a bowling ball are tossed at time 0 off the roof of a skyscraper. The tennis ball has a horizontal velocity of 5 meters per second, and the bowling ball has a horizontal velocity of 10 meters per second. If the building is 120 meters tall, then tell me how long until each ball hits the ground? What is the initial vertical velocity of each ball? What is the horizontal displacement of each ball? D, what is the total vertical velocity what is the total velocity? I said vertical. I mean, what is the total velocity? So horizontal and vertical. What is the total velocity of the tennis ball 1 second after being tossed? And E, make a graph of the tennis ball's position versus time and velocity versus time in the Y direction. So what I'd like you to do is give this problem a try. Try not to look at the solutions, and you are free to ask as many questions as you want while you have me here. I'm going to turn the lights back on and come right back.
I've got to go, Mr. Everly.
All right, Zach, I'm going to finish all 3 problems, even if there's no one around. So you can come back and watch them if you would like to.
Okay.
All right.
All right. See you tomorrow.
Good day.
You too. I'm going to give you guys a couple more minutes to see if you can get to the end of the problem. Send me a text message or a chat message when you have finished, so I get an idea of when I should start going over it. Good job, Brianna. I will give it one more minute. I'm going to take advantage of the time and try to get through it before we're out of time. If you guys are able to stay after, I have no issue staying after myself, but if you have to go at the end of the hour, that is fine by me. Okay, so some of these problems are meant to take a long time and some of them are not. So what I like to do with problems like this, especially when they just give me a whole bunch of text, is I like to draw out what is happening. So we have two projectiles, two balls that are being tossed off of a skyscraper. One's going 5 meters per second, and the other one is going 10 meters per second. So twice as far. Okay. Now, I know certain things about projectiles. Okay. And I know that they fall in a parabolic shape. And so their paths are going to look like this. But also, can someone tell me what's going to be, which one of these two balls, the bowling ball or the tennis ball, is going to hit the ground first?
They will land at the same time.
They will land at the same time. Yes. So the tennis ball is going to not go quite as far because it is moving slower, but the time will be the same. Okay, that's because everything falls at the same rate. And as long as neither ball had a velocity in the y direction, both balls will land at the same time. So that kind of answers part A for me, or that answers part B. But part A is how long until it reaches the ground. So they're asking for time. And I have to think about what I know. So I know that each of these have a Vx, okay, an initial velocity in the x direction. For the tennis ball, it's going to be 5. And for the bowling ball, it's going to be 10 meters per second, okay? And so this is where you guys have the option to set up my projectile motion chart. Now, the chart is not specific for AP. They do it in Regents, and it is also not a requirement. So you will never have to draw a chart. And if you are pressed for time and you think it won't help you very much, you don't have to. But there's so many numbers going on, especially in a problem like this where you got two balls. It's important to keep the X and the Y variables separate. Remember, motion in the X direction has nothing to do with motion in the Y direction. You can never plug an X number into a equation with Y numbers and vice versa. So keeping this straight, I like to put it in this box, but if it's easier for you not to, as long as you get the right answer, it doesn't matter to me. It's also a great place to list out all your numbers with units so that you don't get in trouble for not having them later on. Either way, so let's take the tennis ball and let's plug in everything we know. 5 meters per second is the speed they gave us. What's the acceleration for a projectile in the X direction? Someone answer that question for me.
0.
Yep, it is 0 meters per second. And what is, oh, I did X and Y. Oh no, this is supposed to be Y on the bottom, and this is supposed to be X at the top, which is why I'm writing it the way it is. Yeah, 5 meters per second, the X direction, 0 for A. And now we're back on Earth, unlike the first question. So that means our Y acceleration is going to be, again, negative 9.8 meters per second squared. Now, we kind of answered B already. Both of these balls are going to have an initial velocity in the Y direction being 0. Neither of the balls are thrown upward or downward, so there's going to be no Y component to each of them. So therefore, we have a 0 initial velocity in the Y direction. Now, both of these objects are going down 120 meters, because that's the height of the building, 120 meters. And so that is going to be my displacement. And when I'm talking about final velocity, I'm referring to the speed right before it hits the ground. Be careful not to think, well, it stops when it hits the ground. That's not what they mean. They want to know, when they're talking about final velocity, how fast it's going right before it hits the ground. But we don't need that to answer this question, because now we have displacement, initial velocity, and acceleration in the Y direction. So we can solve for time. And time for the tennis ball is going to be same as time for the bowling ball. So I can use dy equals VIY t plus 1/2 AY t squared. Now, plugging in all the little y's next to my number, next to my letters, is a good way to remind myself to use Y variables, but it's not required if you're doing one of these problems. So don't think you have to put the little y's or the little x's in when you do the AP exam, but it just helps me keep straight. I'm plugging in Y numbers, can't plug in X numbers. So 120 meters, or negative 120 meters, is equal to, this initial velocity thing goes to 0, plus 1/2 negative 9.8 meters per second squared, times the time being what we're solving for. And so I can multiply this by 2 and then divide by negative 9.8. So negative 240 divided by negative 9.8, that's going to give me my time. Negative 240 divided by negative 9.8, giving me 24.5 seconds, 24.5 seconds. So that's part A, how long it takes to reach the ground. And I already answered part B. Both of them are going to have an initial vertical velocity of 0 meters per second. So then we can move on to C. What is the horizontal displacement of each ball? So that's pretty easy. So let's go up to the chart. I have the time now, so I can plug in 4.5 seconds. And I'm solving for displacement in the X direction. So now I've got time and I have speed, and acceleration is 0. So I could use any equation that has displacement in it, and I should get the right answer. So displacement is equal to VIT plus 1/2 AT squared. The acceleration is 0, so I can cross that off because I'm only plugging in my X numbers. dx is equal to, for the tennis ball, 5 meters per second, times the time, 24.5 seconds. That gives me a distance of 122.5 meters. Then I can just repeat the same thing for the bowling ball, which is moving at 10 meters per second. And the time is going to be the same. And so that's going to be 245 meters. And so that's the answers to part C. Right, flipping it over for the backside. In part D, it wants the total velocity of the tennis ball. Now, this is going to be the hardest thing. It wants the total velocity of the tennis ball at time equal to 1 second. So whenever they change the time on you, you have to start with a new chart, because we're no longer talking about the initial position going down to the final position. Right now, we're talking about this going down 1 second later,
not being at the bottom yet, being somewhere on its path. And so certain things are going to be the same. So X, Y, D, V, I, V, F, A, and T. Certain things are going to be the same. What are they asking for? Tennis ball, tennis ball. Okay. Certain things are going to be the same. For instance, the initial velocity will be the same, 5 meters per second. The accelerations are going to be the same, 0 meters per second squared, negative 9.8 meters per second squared. All those things will be the same, and they gave us times equal to 1 second. The initial velocity in the y direction will still be 0, and the rest we do not know. They want the total velocity. That means they want to know the velocity in the x direction and the velocity in the y direction. And then connecting those two vectors with a triangle is going to give me my total velocity. So that's what they're looking for right now. So I need to know what both of these are, so I know the sides of my triangle. So I'm going to draw it again. This time I'm going to use it to label the different sides. My Vx is easy. It's going to be 5 meters per second. That's the initial velocity in the x direction. The Vy is a little bit harder. It starts at 0, but in 1 second, I want to know what is the velocity at that point. So I need an equation that uses Vi, because I have it, Vf, which I'm looking for, A and T, which luckily there's a really easy one. Vf equals Vi plus A T. So solving for Vf in the y direction, 0 meters per second plus negative 9.8 meters per second squared times the time of 1 second. That gives me negative 9.8 meters per second as my speed or velocity in the y direction. So I can plug that in at my triangle. And so I got 5 meters per second in the x direction, 9.8 in the y direction. Finding the total, I just have to use Pythagorean theorem, a squared plus b squared equals c squared to get that side of the triangle. So 5 meters per second squared plus negative 9.8 meters per second squared, and square rooting that will give me the total velocity that I'm looking for. 5 squared plus 9.8 squared, all square rooted, gives me 11 meters per second. Now, you normally would have to find I think that I forgot to ask something on this problem. And normally you would have to find the angle in order to get the total velocity. So if you're able to find this angle and communicate its magnitude, that would be a more complete answer. Because if they're asking for, oh, I'm dumb, because the problem asked for speed, if I'm correct. Where's the thing? It's literally right here. Okay. So what is the total velocity? Oh, so if it's asking for velocity, we do need the actual angle. And so you can use any trig function you want because we have all 3 sides of the triangle. I'm going to use tangent because if I made a mistake finding the hypotenuse side, then I'd be in trouble. So tangent's opposite over adjacent. So tangent of theta is equal to the opposite side of my angle, which is 9.8, divided by 5 meters per second, which is my adjacent side to my angle. And so if I inverse tangent to get the angle by itself, my angle is going to be second on the calculator, tangent of 9.8 divided by 5, giving me an angle of 62.97 degrees. Can anyone tell me what
is the direction of this angle? How do I end it up? 62.97 degrees. I have to give it a compass direction. All I heard was a dog barking.
South of east.
Yes, it is south of east. South of east. Or you can write out south of east. That would be good. You have to start with one of the four directions and move toward the line you're trying to describe. So this angle here is 62.97 degrees south of east. Okay. So that gives you the velocity. Most of the time, they're just going to ask for the magnitude of a velocity. If they ask for the magnitude, that means they just want 11 meters per second. They don't need you to calculate the angle. But if they ask for the velocity and they don't ask for just the magnitude, then you're going to need to calculate the angle. So last part of the problem. Make a graph of the tennis ball's position versus time and the velocity versus time in the y direction, okay? So again, position versus time graph and velocity versus time graph. For a object that starts here and then falls down, kind of like this. So this one's going to be displacement or position, either one. Time and time. Okay, so looking at this object falling, its vertical position starts really high. It starts 120 meters above the ground. So we're going to start this graph at a very high position. And then it's going to fall slowly at first, so kind of a shallow line. And then it's going to fall faster and faster and faster. So it's going to get steeper and steeper and steeper as we go. And so our graph kind of looks like this, okay? And it would continue if it didn't hit the ground. It would just continue in the negative direction. But I think the negative displacement would be going into the earth. Now, for velocity versus time, we initially start, they're asking about the y direction. So we're going to start at 0 because the initial velocity in the y direction is 0. And then it's going to get faster, but it's going to get faster negatively. So it's going to get a larger and larger negative velocity. So that means instead of going up as it gets faster, it's actually going to go down as it gets faster, as the velocity gets larger and larger in magnitude, but further and further down in the negative direction. So that's what the two graphs will look like. So we obviously ran out of time a couple minutes ago. I don't want to hold you guys up forever. I do, however, want to give you guys the option. I'm going to be here once you guys log off, or if you choose to stay, I don't really care. I'm going to go through that last problem just so it's on the video for everyone to watch if they want to. But before we do that, I would want to open the door for anyone to ask any questions they have about the AP exam or about kinematics or projectile motion in general. So does anyone have any questions they would like to talk to me about? Any concerns at all? Okay, so at this point, if you have better things to do, you are free to log off and do other things. I'm going to keep going here and record going through that last problem. So if you want to do that with me, you're welcome to stay, but otherwise you don't have to stay on. And it's Max who's still here, but maybe not for long.
You know what? I'll just watch it later.
That's completely fair. I'll see you later, Max.
Have a good afternoon.
Yeah, you too.
Okay, so again, no one needs to feel bad about leaving. I promised an hour and I planned way too much stuff. But in case you want to have this problem as something you're studying with, I want to make sure I walk you through the solution. So I'm not going to spend a whole lot of time going through this, but I think it's at least important to understand the basic ideas in this problem. So Fred is taking a trip to his local supermarket. To get there, Fred needs to travel 240 meters north, 135 meters east, and 290 meters south. The store closes in 5 minutes. Oh boy. So A, what is the total distance and total displacement Fred will have to travel? B, what does Fred's average speed and average velocity need to be for Fred to make it to the store before they close? I wanted to include a little bit of a line that says that, yeah, you don't have to have any time left over to do the shopping. You just have to make it there right before they close. C, if Fred could walk in a straight line from his home to the store, what direction would he have to walk? D, Frederica gets to the store in a different way. Her position versus time graph looks like this, and it's this ridiculous curve. Very hard to see everything here. Can I zoom in? You should have a copy of this for yourself on the Schoology thing. Either way, so his position versus time graph looks crazy like this. During which interval of time is Frederica accelerating, moving at a constant velocity, or remaining still? Sketch a velocity versus time graph for Frederica's journey. 3, how could you draw a line to represent Frederica's average velocity on the graph above? And 4, is the store in the positive or negative direction from Frederica's house? Okay. So let's go through the solution to this. All right. So looks like this. So the first thing I wanted to map out where he was walking. So he walked 240 meters north, 135 meters east, and 290 meters south. And so he did this square box shape and did a dotted line like this. So he went slightly south and pretty far to the east. And so basically his displacement looks like this, where he had 135 meters east, and the difference between the 240 meters that he went north and the 290 meters that he went south is negative 50 meters. So that's 50 meters south. And so I kind of combined that into a triangle, 135, 50, a squared plus b squared equals c squared, and c squared was 144 meters. So to recap for the final answer, the distance, the total distance he traveled was 240 plus 290 plus 135. So that's his distance north, his distance south, and his distance east, adding up to a total distance traveled of 665 meters. His displacement was much smaller, okay? Because of the triangle I showed you before, he only traveled in total 144 meters in a straight line. So 144 meters, and then that gets to part B, which asked his speed and his velocity. Well, what you do then is you take, whoa, that's upside down. A little hard to see. Okay. So what you do then is you take the distance over time. So total distance was 665 divided by 300 seconds gives me 2.22 meters per second. The velocity was displacement over time. So instead you use the 144 and divided by 300 seconds. Now part C asked us specifically, what direction would he be traveling if he only traveled these 144 in a straight line? And so for that, you have to calculate the angle. So again, I use tangent. The reason I use tangent, even though I think most people find it harder, is because tangent's the opposite side and the adjacent side. So opposite over adjacent equals tangent. And these two numbers I normally have
from the beginning of the problem. And this number I normally have to calculate. So I don't want to use the number I calculated just because that just increases the odds I make a mistake somewhere and get more things wrong. You can use whatever sign you want, but I find it's generally safer to use tangent. Anyway, so tangent of theta is equal to 50 over 135. Doing second tangent to solve for the angle, 50 over 135, inverse it, you get 20.3 degrees, okay? And so 20.3 degrees, we start at east and we go south to get to the line. And so therefore it is south of east, like that, okay? So my velocity is 0.48 meters per second south of east, because I did the total displacement over total time. And the angle that I'd have to travel is 20.3 degrees south of east. Now, looking at this crazy graph, this is a position versus time graph. The different intervals of time are A to B, B to C, C to D, and D to E. And I wanted you to identify what kind of motion Frederica was doing during these walks. So from A to B, she's clearly accelerating. She's doing, you can tell because the line is curved and it's getting steeper, so therefore she's getting faster. Even if it was something like this, she'd be gaining speed just in the negative direction. So if the line gets steeper, she's getting faster. The line gets flatter, she's getting slower. Something like this, where it ends up quite flat. Anyway, between B and C, she's clearly at rest. She is clearly still. She's not going anywhere. Her position is not changing. Her position is maintaining the same value the whole time. Now, C through E, she has a constant negative velocity. Okay? So, constant negative velocity, meaning that it is a negative slope. And remember, slope is equal to velocity. Okay, like that. And so, since it's going downward with a negative fashion and it's not curving, it's a constant negative velocity. Okay, and so that's what I have here on the answer key. A to B is accelerating, B to C is at rest, and both C to D and D to E, it's constant negative velocity. And the last thing it asks us, well, it wants us to sketch a velocity versus time graph for Frederica's journey. So this is a little bit complicated. So we set up a velocity versus time graph. If we look at the chart we have here, so that first A to B time, she's accelerating. So I want to show what acceleration looks like on a velocity versus time graph, which is constant slope. That's acceleration. Then she's at rest, which means we don't have a velocity, we have a zero velocity. And so the line looks more like this, where it is very flat along the zero line because we have zero velocity. Then from C to E, we have a negative constant velocity. Therefore, that's what I like to draw. I'd like to draw something below the zero line, so something negative, and something constant. Okay, remember, a flat line like this on a velocity versus time graph is constant velocity because the value does not change as time moves on. Okay, I know it's slightly slanted, but that's just because I'm a bad drawer. Okay, how could you draw a line to represent Frederica's average velocity on the graph above? Okay, so on this graph above, which I redrew here, the average velocity is going to be the average slope. Okay, sometimes in graphs, like the graph can be quite crazy. And sometimes the only way to find the average of something, say this was, let's say it is something easy, like velocity over time. If it was velocity over time,
Then the slope would be acceleration. So to find the average acceleration, you would connect the starting point to the end point and find that average slope. That would give you average velocity. For Frederica's trip, it was a displacement versus time graph. So the slope gives you the velocity instead. And so the initial point is at the 0 line and the final point is way down here. And so the average velocity for the whole time is going to be the slope of this line. So you drew that line and basically stating that the average velocity is equal to displacement over time is equal to the slope. And that is good. Okay. And then the last question, is the store in the positive or negative direction from Frederica's home? Well, it starts here at 0, ends at a negative location, so therefore had to be in the negative direction because she went negative overall in her journey. So I hope this question makes sense. If you have any questions for me about kinematics or any of the problems we went over today or about the AP exam, send me a message. I am going to be a constant resource for you guys throughout these last couple of weeks. Let me know if there are any issues, and I will see you later.